I'm from Continuum Analytics. How many people in this room have heard of Anaconda before? A few? A lot? How many people are using Anaconda? Quite a few. Okay. The people who aren't using Anaconda, we're always interested coming to these events and hearing about like why Anaconda isn't the right thing for you as somebody who's interested enough in like Python to be giving up your Tuesday night to be at a Python meetup. We really are genuinely interested. I'm not going to try and like convince you or tell you why you should be using it. I just want to hear from you. So hopefully we can share a beer afterwards. So for people who are like following along, I try and maximally do things in an interactive way. I am actually going to flip through some slides to give like the slide version of the story, and then we're going to look at this topic through some Jupyter notebooks and through code. There's not a lot of people with computers here, but so if you have one, you can go to one of those URLs. Maybe I can post them on a comment on the meetup site, or you might just be able to remember them, bit.ly/scaleml-dask-workshop. You only need to remember the first one. It's got links to the second one inside of it. Close. Don't save. All right. Are there any Canadians in the room? Any Canadians? Canadians? No Canadians. All right. I'm Canadian. I flew in direct flight from Toronto, landed this morning. I'm here till Friday morning. And if anyone, tomorrow's my one free day. If anybody has suggestions for what I should do for my one free day in Munich, I am staying with some friends from Munich, so hopefully they'll also have some suggestions. But anyway. So next question, how many people here have heard of Dask before? What's like the visibility of Dask as a thing? Limited, so like I see less than a dozen hands. So of those dozen hands, how many people have actually tried to do something with Dask, have like tried to use Dask? One tentative, it went up, went down. All right, so Dask is pretty awesome, and I hope you're going to get pretty excited by it tonight, and you're going to feel motivated to, one, start using it and some of the great stuff that's already built into Dask that you can use it for today. In particular, parts around Pandas, NumPy, a little bit on Scikit-Learn. So I'm going to kind of, that's usually at the end. I'm going to jump to it more in the middle for time reasons. But additionally, one of the key things I want to tell you about Dask is that so Dask, now you're going to get more and more questions. I was trying to make this interactive. It can't be interactive with you with laptops in front of you, so maybe that's better because you're looking at me. We're going to try and have a conversation about this. How many people here have heard of Blaze before and the idea of Blaze? 1, 2, virtually nobody. Okay. All right, so we're going to connect the dots in just a second. How many people here are familiar with NumPy and have used NumPy? A ton of people, like practically everybody in the room. Okay, so NumPy was created like practically 20 years ago by Continuum's founder, Travis Oliphant. And it's foundational, as we all know. Like if you're using it, you know it's foundational to computational science and Python today. Continuum as a company was created not for the sake of Anaconda. Anaconda was like a necessary byproduct. Continuum as a company was created to make the next generation NumPy. And the next generation NumPy, it's not a secret, it doesn't have a code word, its name is Blaze. But Blaze is like, Continuum's into like year 5, and Blaze is not ready yet. But on the path to making Blaze a thing, and so the objectives with Blaze was to be able to have distributed out-of-core computations, to have all the amazing stuff you can do with NumPy, to be able to do that kind of thing on a distributed infrastructure, to be able to do out-of-core processing, so delayed processing, batch processing to process data off of disk or from a database, something that could be really flexible for distributed data sources, something that could be data aware because we all know we live in a world now easier to move your computations around because your processors all look the same, but your data is different and it's spread across like lots of machines and storage servers and things like that when you're dealing with like properly big data. And so that was like next generation NumPy, and the name for next generation NumPy is Blaze, and we're still working on it, and there's other people who are contributing to building next generation NumPy, and Blaze is that thing. But on the path to building next generation NumPy, we've ended up creating Dask, and Dask is a distributed computing framework. So we're going to see two things today. First of all, we're going to get a sense of some of like high-level capabilities. We're going to get an idea of what like Dask does and how it works. And we're going to do that through the lens of NumPy arrays that we're probably all familiar with. It looks like everybody here has used them before, so you're going to be familiar with the syntax of doing like NumPy-like things. But instead of it being on a NumPy array, it's going to be on a Dask distributed array. And the other, I'm not even going to ask for hands up on this one because I'd be insulting you at this point with the other questions I've asked, is pandas. And so obviously if you're all using NumPy, like sometimes I'm in audiences where like tons of people everybody knows pandas and like hardly anybody knows NumPy. And I'm like, do you know that pandas is like built on top of NumPy? And they're like, didn't know that. But same story with pandas, that pandas, there's a distributed parallel version of pandas that's available through Dask that basically wraps, it's not a re-implementation, it wraps pandas data frames. And so like 90% of what you can do on a NumPy array or on a pandas data frame, you can do on a Dask distributed array across a network of machines, or you can do on a Dask data frame, which is a network distributed pandas data frame. So we're going to look at those, and those are going to give us some insights to how Dask behaves. We're then going to look at how those have been applied to parallelize some other algorithms. So we're going to look at a really simple example. For time reasons, we're going to look at cross-validated grid search, Scikit-Learn cross-validated grid search. It's kind of like the most, like barely saying you're doing parallel machine learning. I mean, you are doing parallel machine learning, but the thing is that cross-validated grid search, common problem for people who are doing machine learning algorithms is like parameter sweep. You've got to like figure out like what are the right parameters. We had these questions earlier about like, is 300 the right number? And sometimes your questions are like, we've got a value and it goes between 0 and 1, or it goes between 0 and 10, or whatever, right? Like you've got a bunch of parameters for your models, and you got to figure out what are the ones that are going to give you the best results. You've got a bunch of training data, you've got some testing data, and you've got to figure out like what are your good parameters. And if you've got a lot of parameters, then like figuring out the right parameters for your model when it's actually like running, that's like a big challenge. That grid search thing is a big challenge. But what's the advantage that we've got? So I'm going to give an opportunity for somebody to actually not just put their hand up, but to use a few words to make sure you're paying attention, and for somebody to show off their knowledge of machine learning. What is the great opportunity that we have when we're doing a parameter search for machine learning algorithms for performance improvements? So who wants to give me an answer? I'm going to wait till somebody gives me an answer. It doesn't have to be the right answer, but I'm going to wait till somebody gives me an answer. So we want to improve the performance of our machine learning algorithm on the training stage, not on the execution stage. What we're looking at is figuring out what are the right parameters. We're choosing from a whole bunch of parameters, and right now it takes us, like, for example, 7 hours. It takes us 7 hours. I'll come back to that maybe if I find the right opportunity for Marco's earlier talk. What can we do to improve the performance on something which is doing like parameter selection? Okay, I hope you guys warm up for me. Oh, somebody here, thank you very much. You've rescued me, yes. Speak loudly and I'll repeat it. That's right, you can totally parallelize the grid search. So each of those tests of a particular parameter set is completely independent from all of the other tests. So that's one part. And then a cross-validated grid search, if you know anything about the way cross-validated grid search works, is rather than doing like your testing set and your training set and having those like fixed, you basically like create a bunch of buckets, and then you basically like iterate through which buckets you're using as a test set and which buckets you're using as a training set. So they're actually like two levels in a cross-validated grid search, both in terms of how you split up your like available data set into test and training, and then how you do your parameter suite. That gives you huge opportunities for parallelization. So we're going to look at how Dask can be used to, has been used to parallelize that. Okay, so I've been talking for a bit now without actually showing you stuff. Let's go through the slides. I'm going to go through these pretty quickly because we're going to come back to almost all the interesting slides you're about to see on the screen here. We're going to come back to in a Jupyter notebook where we'll actually execute them. So be prepared, but hopefully also get the sense that I would like this to be interactive. If you've got questions, just put up your hand, or like I was doing, whether appropriately or inappropriately for the last speaker, just sort of shouting out questions. You can also just shout out questions. You're welcome to do that. Okay, so we got this amazing analytics ecosystem, NumPy, Pandas, and like everything that's built on top of them. But boo, so that's like the yay part. But then the boo part is it's mostly restricted to a single core and RAM, because they're single. Python is single-threaded. Python doesn't like automatically do any parallelism for us, and these Pandas is built on top of NumPy. NumPy is like wickedly fast, written in Fortran and C, and can leverage other libraries that are like hand-optimized machine code. We use you get Anaconda, you get the Intel Math kernel libraries. It'll on like a recent Intel processor. It can give you like an order of magnitude speed up for like just for those core numerical routines, because Intel wants you to buy their processors, and so they put out these like great, but all single-threaded, right? So the question is, how do we go and parallelize this whole ecosystem? Anaconda from Continuum is like the thing we're best known for, and it is this thing that brings together all of these great tools and libraries. And we want to like say, 2017, how do we parallelize this stuff? Yes? Yeah, loudly over the, because you got to be over the fans and stuff. Yeah, that's right. So some libraries have built-in parallelization in them. You're quite right. So if they've got built-in parallelization, we don't need to worry about it. We're thinking about how do we parallelize stuff, how do we provide the pieces that allow us to parallelize the infrastructure. Thousands of packages, lots of custom algorithms built on top of them. Oh, I see. Okay, so the question, I'll repeat the question. The question was, what about things like XGBoost, which are already parallelized? Well, they're in the minority. Most libraries, like they're not parallelized, and people would prefer not to write their own parallelization stuff like from scratch. Is kind of the short version, sort of the short version of the answer to that question. Okay, we can talk about it. Ask again if you want to follow up, but ask again at the end, or ask again over a beer when we break up. So we see lots of examples of. Trying to get that a little bit bigger for you. Lots of examples, scikit-image, scikit-allel, lots of opportunities where parallelization is possible. We want a parallel computing library that's flexible enough and familiar enough to parallelize lots and lots of code that's out there. So lots of different people can pick stuff up and say, hey, I'm going to go and implement parallel implementations of things. So Dask has ended up like evolving into being like that thing. So we're going to look at NumPy and Pandas. We're going to talk about task graphs and task scheduling. Briefly, I probably won't talk about Spark and Airflow. So yeah. All right, so this is a really important picture. Dask arrays give you a synthetic view of a whole bunch of NumPy arrays. So what we have here is a picture of 4 by 5 array of arrays is basically like the best way to put it, where we've got like here a little NumPy array, and every one of those blue squares, and I'm sorry, blue on black is hard to read, but hopefully you can see it well enough. So we've got in total like 20 of these NumPy arrays, and they are just NumPy arrays. And then Dask provides a synthetic view of those individual NumPy arrays. And it knows where they live, what machine they're living on, knows how big they are. And so it's able to then act as that shim, act as that interface for operations. So we could see in the example code here, if we were to go and create a random array of 1,000 by 1,000, we'd call it like this in NumPy, and then we could do a single value decomposition on x transpose. In Dask, it's almost exactly the same, but we're able to do it on a lot bigger size. So here we're looking at 100,000 by 100,000, and we specify how we chunk it up. And there's different ways we could create this synthetic NumPy array in terms of like building it so it is kind of like odd sizes. They need to fit together in a hypergrid effectively, but they don't have to be exact sizes. But here's like an example of how built in to the Dask array, random.random, not the NumPy random.random, we're able to create a 100,000 by 100,000 random array of values where each NumPy chunk is 1,000 by 1,000. And so you can Do the math on that, there'd be like, I think if I'm doing it right, 10,000 of those. And Dask will automatically look after distributing those across the resources in the Dask cluster. And we'll come back to where does your Dask cluster. I've played with Spark before, and it was a painful experience because the code examples looked so simple, but then nobody told me all the work I had to do to get like the Spark cluster set up and the Spark context configured and things like that. So we'll come back to that part later, but the short version is that like Dask does a bunch of it for you automatically, and it's super simple. And then how do you do an SVD? Same thing. You do an SVD, Dask array, linalg SVD, and then you do the dot. Yes?
I'm really sorry, but
don't apologize. How are questions?
Yeah, I still can't understand the use case, because like if we are parallelizing across a Hadoop cluster, across a Spark cluster, whatever, then our problem wouldn't be with NumPy. Our problem would be with parallelizing the gradient descent or whatever we are using. But if we are using a machine learning library that is not parallelizable itself, why do we need to parallelize the NumPy? So like, where
that is such a great question. Why do we need to parallelize NumPy? Well, if you're doing like something, if you're doing linear algebra operations on a large synthetic matrix, then this is super useful, okay? So number one, if you're just working and doing normal stuff with NumPy arrays, if you're out there writing NumPy code and doing like vector operations and selections and subselections on NumPy arrays, then the Dask array will let you go out of core. It'll let you do things in parallel. So it'll let you leverage all the cores on a single laptop. It'll let you use all the cores on a machine. However, the question that our colleague here has asked is a brilliant question, and I'm going to answer it in a few slides, okay? I'm going to come back to answering that exact question. So a Dask data frame, same idea, but data frames aren't like arbitrary size, they're tabular-like. And so we have so here we can imagine CSV files, say, that we're reading in, and each one is for a month. And we've got January, February, March, April, May. Each one of them is a Pandas data frame. Say each one of them is like 5 gigs. In memory, say it's something like 15 gigs in memory. Well, we can, like a whole year of that is more than we probably have, more RAM than we have in a single machine. But if we got a whole bunch of machines, then we could have like one of those in each machine. And so the Dask data frame similarly gives us that synthetic view that will look like a data frame, and it will look after the distribution of operations in parallel across all of those distributed data frames. So first bit of code here, this is like bog standard pandas code. We do a read CSV on a single CSV file. We parse dates from the field called timestamp. And we can then do a group by based on the timestamp hour, and then we can get the mean of whatever the heck value is. But say that's like close. Say it's like the hourly. Say it's ticker data, and this is like the close for each 2-minute, 5-minute block, whatever it is. We do a lot of work in financial services. There's probably, how many people here are in financial services? I don't know if there's a big financial services community in Munich. A few, okay. So we make a lot of money in financial services. So we have a lot of examples that are like finance-based. And anyway, Pandas is heavily used in that domain. So let's move on to Dask data frame. The Dask data frame, what's the difference here? There's only 2 differences. One is that when we read in a file, we don't have to read in a single file. We could specify HDFS. We could specify like a globbing operation that'll pull in a stack of files, like 12 or like 365 or like 20,000 of them. And Dask will be smart about it, and it's not going to make one machine try and like glom all those things together. It's going to distribute that operation across the network, and it's going to be HDFS aware in this particular example. So it's going to do it on workers where that data is available. Or it could just be on a shared file system, and it's just like lots and lots of files. And anyway, you just put a star in there, and you're then going to like automatically get this synthetic view of this big data set. Now, what happens if your star slurps up files that like don't go together like this? You're going to get an exception. It's not going to work. Like don't do that. It's like don't put a PNG here for read CSV. Okay, so some parts you got to get right, but no more right than you had to get them with Pandas. And we'll come back to the one other difference here, which is this compute operation. It's because Dask and the Dask infrastructure makes use of lazy evaluation and returns futures so that you have you execute the task graphs that you're building for the operations that you're trying to do on these synthetic data structures that you're like putting together in these expressions at the latest possible point. And if that didn't mean anything to you, we're going to see lots of visual examples of this. To your question, many problems aren't just big arrays and data frames. The Python community writes clever algorithms. That's exactly the point that your colleague here was asking. Here is a simple one that is comprehensible and is not addressed by NumPy or Pandas. I look at it and I still think that there are like NumPy-like ways you could kind of address this with like where, but anyway, let's like leave that to the side. So we have a results dictionary. Big A and big B are vectors. They are iterable things. They've got a bunch of things in them. We're going to then iterate over everything in each A and everything in each B. We're then going to do a comparison of those pairs across every single possible like Cartesian join of every possible pair. And under one condition, the results that go into our dictionary for the AB pair are based on the function f, and if it's not that condition, then the results for that same pair are going to be calculated from G. So sometimes the results will be f, and sometimes the results will be G. The values for any AB pair are independent, but they're not, like this isn't like a Pandas or a NumPy problem. So how is this addressed with Dask? So this is just a simple first example of how you today could parallelize your own code. Like this, if you had A's and B's, and in fact in the tutorial version of this, we give you like some A's and B's and a simple F and G function. All that you need to do is create a wrapped version of the function f and a wrapped version of the function g so that they become lazily evaluated. And so a function that just does your f and g function, that just does its thing as you wrote it as a normal Python function, now with this wrapper, now becomes something which is going to be lazily evaluated. And so what ends up going into this dictionary? What ends up going into this dictionary are the futures for those lazy evaluations. How long does it take to invoke this? Like basically as close to 0 time as possible, because it doesn't actually call the function. It just gives you the closure of the function plus the parameters, and it stores a reference to that closure inside the dictionary. And so these things are small, and these things are computed, like you can go through a lot of stuff very, very quickly. You then, that compute method that we saw here, and again, like I said, we're going to see this live, so it's going to be a little bit more meaningful. This compute method that we called, so here we just do mean and we get the value back. Here, that mean, calling that mean function on our Dask data frame, so df here is from a Dask data frame, calling mean there, that's going to return a future. It's not actually going to have a value until we explicitly say, hey, go on and compute that task graph that you've built up. There's the method version of it if you've got something which is already a Dask object, but we can see here that our results dictionary is just a regular Python dictionary. And compute is going to go and iterate through that iterable. And it's then going to look for every Dask delayed object, and it's going to like call the compute method on it. And so then we like reassign our reference to the actual results that we get out. So you've already learned enough that you could parallelize code where you've got independent code. This follows the pattern of the really nice new Python 3.6 async and I think there's some concurrent futures model.
But
yes?
Maybe I didn't understand the example at all, but in this example you wouldn't gain from parallelization because all your resources would be wasted for shuffling. Because since you do the file Cartesian product, you still need to bring your data to the master for reducing them.
Right. So there is some more nuance to this, but if f and g take a non-negligible amount of time to compute, say they take a second to compute, the data shuffling can be a much smaller piece. If a and b here are themselves Dask objects, then Dask will do those computations because the computations can happen anywhere. It will do those computations in a data location aware manner. So it will execute f and g on the a and b pairs where a and b are available.
But then, do I have any opportunity, like for example in Spark, to control for partitions and for location of this partition?
You're now asking questions I don't know the answers to. Ask on Stack Overflow, post tag it with Dask. Okay, I'm not part of the Dask team, but you've just hit the line where I can't even begin to imagine the answer to that. Okay. Yes. You're supposed to do this.
Thank you. Sometimes what I want to do is like, I want to do this on big arrays, but then I want to evaluate and just do it on one element so I can check if it puts out the right thing before I go on and do it on the big, 1 million times 1 million array. With the compute, can I tell it show me the money, and then essentially if I like the little example it gives me, do it on everything.
Yes. Is the short version. There's a little bit of work you'd need to do, but yes is the short version, okay? Dask APIs produce task graphs, so as you execute things on Dask-like objects, you're building up a task graph. What does a task graph mean? So if you're not a computer scientist, that probably doesn't mean a whole lot to you. Dask schedulers then execute the task graphs. What does that mean? Well, we're going to see I think the visual examples we're going to see are going to tell us about that. So we look at a really simple example here. Just look at the code to begin with. When we do numpy.ones, 15 of them, we're going to get an array of 15 numpy float objects that are all equal to 1.0. When we go and do the same thing with a Dask array.ones, same size, chunks of 5, we're going to have 3 partitions in total. Now, these are teeny, right? You'd never do anything with Dask on this size. We're doing it in this size so that the task graphs that we're looking at are comprehensible, and so we can look at code output and make sense of it. But the Dask version of this would basically, it would exactly create 3 separate NumPy arrays. The first 5, the second 5, the last 5. So it would create 3 NumPy arrays. What do we see here? Here is the task graph that is created. Now let's say that this wasn't 15. Let's say this was 15 million. So let's say this was 15 million and this was, say, 5,000, 50,000. Pick a number, right? You divide one by the other. That's how many chunks you're going to get. Now, the operations to create those, ones are there's not much. There's memory allocation and there's a malloc and a write operation is the underlying operations that are happening there. In this case here, with these 3 chunks, we can do 3 parallel ones. So we do a numpy ones for 5, we do a numpy ones for 5, we do a numpy ones for 5. But we don't actually execute that thing. We just have the futures for the task graph that is ready to execute. So X that's been returned here is not an array with a bunch of ones. We haven't allocated 15 64-bit integers. We have created a task graph which has 5 independent nodes that can be executed independently when it's time to execute them that are ready to go and do this operation. What happens if we do a .sum operation? So sum is across everything. So we now add, by doing that x.sum, what does this return? This returns a new task graph. It iterates on the task graph that already exists in X, and it says, now add a sum operation. And so here's what we started with. And we now add a sum across each of those chunks, and there's the results. And then because a sum executed like this is a sum across every element to give us a scalar, we then have to do an aggregated sum at the end. And so this is now our iterated task graph. Now, what if we were to do instead, we've changed now to do a 15 by 15 matrix. We got a 15 by 15 matrix with 5 by 5 chunks. So it means we've got 9 NumPy arrays in total, 9 5 by 5 NumPy arrays in total. And so what do we see? We see 9 across the bottom. When we sum down one axis, we're then going to end up with something which is just going to give us a 15 by 1 vector, but it's still going to be in these partitions. And so we can see each of these is completely independent, and what we're going to end up with the end of these is going to be a 5 by 1, a 5 by 1, and a 5 by 1. And we can carry on. So we can do X plus X transpose, and our task graph gets more complicated. Now, for people with linear algebra background, we've got a 9 by 9 matrix. We've got a 9 by 9, let's call it like a hypermatrix, okay? We've got not 9 by 9. 3 by 3, so we've got 9 chunks in total. When we want to do a transpose of that, how do we do a transpose of the overall? It's 15 by 15. But the transposes of the diagonals don't have to communicate with anything else. So there's one diagonal, there's another diagonal, there's another diagonal. So those are the 3 diagonal matrices that don't have any interrelationship. However, the remaining 6, they've got some sharing, they've got some communication that has to happen. And so the remaining 6, we see these other task graphs that have some dependencies that need to execute. Again, this is just on a small scale, but this is giving you a picture of what Dask is doing. It's building up these task graphs. Here we're seeing them on a small scale, but in practice they'd be on a big scale. Big scale, if you've got, yeah, big scale. They'd be on a big scale. And it can keep getting more complicated. So dot product plus 1, suddenly that makes it like a lot more complicated for the layout of the task graph. And minus the mean. And the point is not to be able to read those. The point is just to see that these operations take basically 0 time to execute. They take like single-digit milliseconds because all you're doing is building up the task graph to complete that operation. Now, it doesn't mean you've got the results. It just means you've added a layer to your task graph. And then one last step in that whole sequence. So having created these complicated task graphs, we're now in a situation where we can imagine having, like my laptop has 8 cores on it. We can only start executing 8 of those tasks. Which 8 tasks do we execute? We execute the 8 that have no input dependencies, which are ready to execute. And so then here, the task scheduler manages the progression through the task graph. This is the same kind of technology that like operating systems have been using since like the 1960s. Okay, it's very well established ground for how you create things that can process these DAGs, how you construct these task graph dependencies, how you manage them, and how you execute the next piece. Layered into Dask has incorporated pieces that are aware of characteristics around certain kinds of nodes. It keeps track of the computational performance of certain kinds of nodes. So it knows how, it has like an estimate of how long a certain kind of node is going to take because it's already executed like 50 times or something like that. And a sense of data locality. Okay. Map, Spark, and Hadoop do very basic task graphs that they have built-in ideas about. They don't do complicated task graphs. They don't have the capability of doing that. They can map a single function across a bunch of inputs to generate a bunch of outputs. They can aggregate a bunch. They can do like a gather, cast, broadcast, and they can do like a reduce phase. So these are like the kinds of things that Spark, Hadoop are well suited to. And I'm going to jump through these so we can actually get to seeing some code. There's some comments there on other task schedulers. So the message here, you want a task scheduler like Airflow or Luigi, but built for computational tasks like Spark or Fink. So there's a single machine scheduler, there's a distributed scheduler, and they're really easy to set up. And we're going to see those when we actually go look at some code examples. And let me see if there's anything useful to see here. These you just have to kind of like imagine what the colors and pictures mean, but this is just showing how the scheduler, I won't go through the animation that I just clicked through. The client generates those task graphs that the scheduler then holds onto. The scheduler knows the state of the workers, and it then pushes portions of the task graph out to the workers and collects back the results and returns the results to the client. So that little animation is telling that story. Looks like concurrent futures, high-level APIs. Let me see. Gil. Yep. Okay, good. So now, some code. We get to look at some code. Organizers, time check. I feel like we're already way over time. I feel like I started 30 minutes later than I was expecting to start, but now I don't know when I'm supposed to end. How long do I have? Tell me how long I've got.
Time as long as your demo is amazing, and I hope it is.
Okay, so I still have some time. That's great. I love quantitative answers.
No, we don't really have like super strict deadline here, so you definitely have.
Okay, so for this part, because I need both hands to drive, I'm just going to have to yell loudly. Oh, and by the way, since we're coming up to 9 p.m., I know a lot of people have lives beyond Python meetups. I will not be offended if you get up and walk out. So if you do, just please be quiet when you do it. And if enough people do it, then I'll know that's my cue to stop, and I'll just stop talking. But if you do have to go, just feel free to go. So you can get this stuff at github.com/ijstokes/scale scaleml-dask-workshop. All right, now we go into the yelling part. So I can show this off. So Dask comes with some great profiling tools that I'm not going to dwell on, and so I'll get to this part on the right-hand side of the screen a little bit later. If people in the back can't see the fonts, I hate it when I'm in talks and I can't see what's on the screen. Please just put your hand up, I'll say yes, and you'll say bigger please, or just go like that, and I'll interpret that as, I'll say louder or bigger font. We'll get there, we'll figure it out together. Okay, so this is content from a workshop I've done like 3 times in the past 6 weeks. So the whole thing is like a 6-hour workshop with exercise that 3-hour workshop with exercise that you get to do. I'm only going to touch on a few bits. I'm going to kind of like fly through parts of this, get to the interesting parts, and one of the challenges is because of the way. Okay, so this is our code examples. Random integer size 10 by 10 between 1 and 9. So there's our 100 random integers for a NumPy and the array. We now do the same thing with Dask. The only difference is we're doing 60 by 60, we're doing it in chunks of 20. So that means we're going to get 3 by 3, so there'll be 9 chunks in total. So this is analogous to the example we were looking at. Now what happens when we look at the top, we look at the record for the NumPy array, and we actually see a bunch of values, because we actually did a malloc, and we allocated like 100 times 8 bytes, so we allocated like 800 bytes contiguous memory for our NumPy array. Definitely contiguous memory, so that works. And we see the NumPy array, that's what we expect. We do the same thing in Dask, what do we get? Well, we get this future object, and it knows what its type is, it knows what its size is, its like overall size, and it knows how big each chunk is. And it knows that it knows like what it needs to do when it comes time to actually like execute it. So it's got some information about this object. What's the type of the object? It's a Dask array.
Why should we specify the chunk?
Yeah, great question. So it would be an awesome feature for the future for Dask to do like some intelligent chunking for you. It doesn't do that right now. So you have to either build it yourself using, if you need fine-grained control where you want to have like kind of different sizes because you know like what's going in those things and you have an idea about the size of them, then you can build that Dask array. Or if you do chunks, they need to be all the same size this way. There is not an automatic chunking algorithm right now. Okay? Good question. No automatic chunking today. It would be a great feature. It's open source. Go ahead and implement it. You've got lots of good ideas. I'm sure you'd be able to do it quickly and easily, at least a first pass. And Matthew Rockland would thank you. Okay. You know what? I can shift enter with one hand, so I can hold the mic so you can hear me better. So remember, A is now our Dask array. So A 3, 10. What are we expecting? Well, if this were our so 310 doesn't exist in this array, but if we were looking at this NumPy array, it would be our 4th row, and it would be our 11th entry here. But we're not looking at that. We're looking at this thing that I've told you hasn't actually come into existence yet. So you might imagine that it comes into existence if you didn't read the next line. You might imagine that it comes into existence when you call it. You're like, okay, it's being accessed. Now it needs to like block until that thing is computed and then returns the value. No, that's not how it works. It returns the future saying, yeah, okay, here's the future reference to that value. And you can hold on to that, and then you can get that value when you do compute. And when you do compute, you'll get the value when the task graph has gotten to that actual point. But until then, here's just your future reference to that object, and that this is a scalar. That's how you read shape and chunk size looking like that. It's a scalar. So you actually need to run compute in order to get that value back. So we do the compute operation, and then we get back the value. So same story for vectors. We do This is going to be a little bit more interesting. Remember, our boundaries are on like 20s, or on the 20s. And so here we've done a slice, which is the 4th row from column index 15 up to, but not including 25. And so we're going over one of those chunk boundaries. Compute does as much as it needs to do to get you that result. Okay? The compute is going to compute you to that point. And because it's designed to be memory, because it's designed to first and foremost conserve memory, it will compute the values, give them to you, and then not hang on to them. And so there is a persist method that you can call, which will persist the results so that they, once computed, stay in memory, but it's basically like frowned upon using persist. I see the question you're asking. Okay, a different number will not come up. You will always get 6 for this. See 11, 12, I execute again, 13, I keep getting 6. However, that is because it's, when you created it, it saved the random seed. And if you had a random seed, it's not because it's actually saved it, okay? But it's designed to return the same values on multiple invocations, okay? So now here, this is interesting. We can see here that we've got, unsurprisingly, the shape is a vector of length 10, but the chunk sizes are 5. Why are the chunk sizes 5? Because we've crossed that boundary, and we could have those 2 initial chunks could be on 2 separate machines. In any case, they're in 2 separate NumPy arrays, and so we're ending up with that kind of chunk size. If I went and changed this to, say, be 5 to 15, we now get a chunk size of 10 because it can do it all inside of it knows that that slice that we've specified is inside a pre-existing NumPy chunk. So I just have to put that back because the next time I do this, I need it to be the right value. Probably doing it as a new cell would have been a better choice. Okay, so we can do compute. And then what do we get? We get back an array. And by the way, this array, this isn't actually a NumPy array. And at this point here, it's reified a NumPy array, and it's returned a NumPy array to you. A region or matrix, so here we're doing from rows 3 to 5, so 2 rows. So we can see our chunk size here is 2 by 5. So we're going to have 2 chunks that are going to span the boundary. They'll each be 2 by 5, and together they'll create something which is 2 by 10. Compute. And that's just to show, so you actually see it in front of you, that you're actually getting a NumPy ND array. And methods are the same story. That you only get the results back when you actually call that compute method on them. Okay, so here I'm just going to run through this stuff. This is just running through the things I was showing before. Creating these operations. So when we go and do this thing here in the green box, B A transpose times A plus 100, that's just giving us this Dask array object back that we have to call the compute on to actually get a value. And again, that's the same for methods that we would call on it. Now, this is pretty neat. We can do this visualize stuff. So we can visualize our Dask data frames, which is good for while we're developing these things. And so we can see these. You got to have GraphViz and Dot and a few other bits and pieces installed. But if you've got those installed, they're available for Linux and Macs pretty easily. I'm not as sure about Windows. They're available for Windows too, actually. They're available as Conda packages for Windows. When I was doing this workshop, I confirmed that Windows people could get these. You can get these nice visualizations, and if we were to go and zoom in on these, you could actually also read them because they're SVGs that are being returned. So Pandas data frame. So here we've got a Pandas data frame, which is reading in a single CSV file from January 4th, 2010 for AIG, minute-by-minute data. And what do we get? We get back a Pandas data frame. We've probably all looked at Pandas data frames before. This is like the new rendering in Jupyter. 4 columns, 211 rows. We see the column titles, the timestamps. Great. Now, we got the same sort of thing that we can do in Dask. I don't want to do it for 365 days, so I'm going to skip that, but in principle you could. I'm instead going to do it here and just do it for all the days that there was trading in January 2010. And that line there that I just executed, that's just showing there's 19 in there, so we would expect that our Dask data frame is going to be a composite of 19 Pandas data frames. And now this is kind of neat. So this has actually gone in. looked at the data enough to get a profile of the data, so it knows what the column names are. It knows that there are 19 partitions. It doesn't know what the values are. It hasn't actually gone and like parsed that data out yet. But it's got a task graph. The task graph is uninteresting because every one of those is independent, so you've got 19 columns there, and these are just the steps that it takes to read in a CSV file. We can see that it knows how long it is, so it's done some initial operations. I said it hasn't like totally parsed it, but it's done some initial operations. We got 4,000 lines. And then we get columns. We can see the columns. We know the column's name. If we do df.high, we don't actually get those values back. We just get back 114 tasks. And so it's part of a task graph. And we can do some computations of these. OK, I want to get to showing you the profiler and showing you the is that at all interesting? Oh yeah, so here's is just showing that you can still do the normal things you'd expect, because when you do compute, you do get back a pandas data frame after that point, so then you can do your plot operations and get back your plot from your Dask data frame version. So parallelized operations on these. And then close mean, that's the task graph for calculating the mean. Okay, so I'm now going to jump to the Scikit-Learn example. That's going to show us some stuff in the profiler, and then maybe I'll quickly go back to the second notebook and show you some pieces from there. Okay, so I already talked through the starting point for what this example is doing. It's this cross-validation grid search. I'll be right with you just a second. So this is this cross-validation grid search example. There are some helper functions that we're using, but mostly we're going to be using the MNIST data sets. These are like handwritten numbers that have been scanned in, and so this is like a well-known image recognition problem. And so you can get the data through this load digits function that's available through Scikit-Learn datasets. There was a question right there. Was your question? This guy's got a microphone for you. It'll help me too.
When you were reading CSV files before,
yeah.
Before you call compute, but after you set up the graph and everything, if then some of your CSV data changes and then you call compute, this will reflect the latest changes, right?
Nah, I don't think so. I don't know. Good question.
Okay.
Stack Overflow #Dask as your tag.
All right.
Great question. I don't know. It is a good question. I don't know the answer to it. Okay. Okay. So just so people who haven't seen this before get a sense of what an image looks like, this is the kind of thing you're trying to figure out, like what digit is that? And some people look at it and go, well, it's a 2, obviously. And I guess it's a 2, but it's pretty hard for me to read. But so that's to give you a sense. So Python is designed to be a high-touch language, right? Like everybody should be using the interactive interpreter. Everybody should be using IPython when you're doing stuff from the command line. And if you're not already using Jupyter, like go use Jupyter, use it heavily. It increases how much you like touch your code and love your code. If you're doing data science, machine learning stuff, look at your data. Very brief aside, during my master's degree, I was doing speech recognition. I'd spent 2 years working on building these statistical hidden Markov models. I was like, done. I was done all my modeling and done all of my experiments, and I'd built crappy neural nets that didn't work, which is why I'm skeptical about exactly how many problems TensorFlow is going to solve in 2017, because I haven't seen that a whole lot has changed in that domain from the stuff I've read up on. But statistics are reliable, and statistics and hidden Markov models work really well. And I'm like writing up my master's dissertation, and for some reason it comes over me that I want to like listen to or look at my data. I discover that 10% of my data is blank. And like, because I hadn't looked, like in a year and a half, when you're dealing with like thousands of hours of audio recordings, like you don't listen to them. It's just data on disk. You never look at that data. And I never like profiled it, or if I had, it would have been like aggregated. I wouldn't have seen that I had tons of zeros, like stuff that just hadn't encoded properly from CD, that I was like the worst possible training scenario, to feed a whole bunch of zeros into your models and then tell it that it's actually words. Touch your data, look at your data, make use of interactive interpreters. All right, we're going to go through this example quickly because I can tell when somebody's standing here, it means my time is up. So we can do, this is going to be our version for serial compute. So no Dask anywhere in sight here. So executing 3 splits for our cross validations. So we got 3 different buckets, and then we do 10 samples for parameter count samples. We now are using the sklearn parameter sampler to sample from this very big parameter space that we've got here for C, gamma, and tolerance values. We're just going to pick out 10 of those, which is like kind of pathetic for a really big parameter search space. We partition our data, and then we go and actually run this computation. So this is going to take about 30 seconds to execute. I'll tell you in advance, but I'm going to talk through what happens in the next bits while that's executing in the background there. The plot here is going to give us a picture. Oh, maybe I pushed the numbers down so it would run quicker for this example here. So we plot the results for the couple of different parameters, and the higher on this scale, the better. So we've got some good values down here. This is why we do this search to try and figure these out. So now what does a distributed version of this look like? So first of all, we connect to our client. Starting up our client here, we're going to get to see some of this stuff actually execute on the side. We can now push these numbers up, so you multiply the two together. Before we had 3 and 10, so that's like a computational size, let's say, of 30. Here we've got 5 and 40, so this is like 200, so it's almost 10 times, 7 times bigger. And what we're now using is sampling a bigger sample from that sample space. We're picking out 40 of those parameters, and then we've got our cross-validated search across those. And now watch, if it all works properly, watch what happens on the graph on the right when we go and run the execution. So what we see here is those tasks being triggered, the computations happening in parallel. These down here, it's a little hard to see because of the way I've bumped the font size, but this would show all of the different nodes in your task graph and would show how they're completing. Now here, this computation has like one kind of node in the task graph, so it's not super interesting. Some of the other operations, you get really colorful with lots of different nodes and lots of different behavior, and we're now able to see a much more nuanced result from our computations because we were able to parallelize them. So because I understand the cue of somebody standing right beside me, meaning you're done, I'm going to go to here. I'll say thank you. I'll say thank you very much, and there might be some time for questions, and so I'm going to turn it over to the boss.
Yeah, thank you, Aaron. Well, yeah, I hope that we have quite some attention left to do the Q&A session. So let's start with that. I'm sure we'll have some. Yeah.
And there's lots of stickers, and I've got lots of business cards, and if they run out of beer here, I've got a business credit card that can pay for more beer and food for anybody who wants.
So,
as
far as I understood, can I do, what are the requirements? Can I just stick it on top of like a Hadoop cluster and then get rid of all the crappy PySpark stuff that I have now and like...
Yeah, in some scenarios. So what I'd encourage you to do before you make that jump is to go to the Dask, dask.pydata.org. And then you'll get like a read the docs page. And down here at the somewhere on the bottom, comparison to PySpark, right there. You can read up about what PySpark is good at and what Dask is good at, and you can check to see if it's a good fit. There's actually a scheduler that'll schedule your workers onto your, through Yarn, onto your Hadoop cluster, so you can leverage a pre-existing cluster and do Dask computations on it.
And how complex it is to stack it on top of it to get it on
Super simple. Okay. It's the overheads are millisecond overheads, like 50 milliseconds for the scheduler to start up. And
okay.
Very simple code. Download the, where'd it go? Yeah, download the GitHub repo, and the third notebook that I was never planning on showing off, the third notebook that I never showed off talks about the schedulers and scheduler configuration, okay? So that's from the workshop. That was a whole section of the workshop that I was never going to cover tonight, so you can go look at that. Okay, next question.
Oh, this could be really useful for like compressed log files.
Yes, absolutely.
Can it handle that and still have the lazy processing part?
Yes.
Okay. So would you like zip just zip CSV, or would that be?
Yeah,
a
so
special
we
file
have
format?
we have a million downloads a month of Anaconda, and we have like something like 20 million downloads a month of Conda packages. And just last week, I wrote some Dask scripts to do exactly what you were asking, because it's like however many gigabytes of gzipped log files, one line per download, and I needed like aggregated results to know what platforms, what versions, what Python version, and frequency over time. So yes, it works very well.
Ever thought of implementing all of this in GPUs?
What's that? I didn't understand the question.
Ever thought of implementing this functionality on GPUs? Then you basically be competing with TensorFlow.
Yeah, so let me try and remember what the GPU story is. So Dask can very happily interact with GPUs. It's a generic scheduler. So we've got something that we've developed at Continuum called NumPy. And so in fact, part of our, I'm now blanking on which part it is. We have done some development already, which combines NumPy, which will do Python to GPU kernel compilation for CUDA kernels from pure Python code with the NumPy decorators, coupled with Dask. Dask, it's possible to tag workers to say, hey, I'm a worker that has a Tesla K20 attached to me. And then for the task graphs to say, hey, I'm a task node that needs to run on a GPU. And the scheduler will match those up. The scheduler will do that for you. The scheduler will look after those parts. And but there is some intermediates that you'd need to do in terms of structuring workers that would then appropriately encapsulate your GPU at the right level for the parallelization on the GPU. But it's totally possible, and we've already done work on that way, and you too could do more work in that direction.
Hi, how would you differentiate Dask from TensorFlow in general?
TensorFlow is a very specific neural net building system, basically, for building network computations. The Dask tasks can be methods, not just number flows, and they can be arbitrary code. So TensorFlow has a very specific objective. You can combine TensorFlow and Dask. They don't compete with each other. If you try doing TensorFlow things purely in Dask, that's a mistake. If you try doing Dask things in TensorFlow, that's a mistake. Okay. So I understand why you're asking the question, because you're seeing these networks, but the networks that you're building in TensorFlow are model networks that you're training and building to as a model for analysis, that once built are then tuned and then execute many, many times. And there's a whole process to figure out like what is that network model that you're using. Whereas here, these task graphs, you construct them from expressions and then you execute them once, or each time your program runs, you execute them once, sort of thing. So they're kind of different applications. You use them together. You could totally use them together. Yeah, they don't compete with each other. Okay.